Hi everybody, in this video I'm going to do an example problem involving angular kinematics with a constant angular acceleration. Before starting on this problem, I want to briefly review some angular kinematic expressions. First, we have the definitions of the angular velocity and the angular acceleration, respectively. In the special case of a constant angular acceleration, we have these expressions. I want to note that these expressions come from these definitions in the exact same way that these expressions come from these definitions. The math is exactly the same. We also have relationships here between our angular and our linear tangential quantities. All these relations follow the form tangential quantity equals angular quantity multiplied by the radius. And the origin of all of those is right here. In one full circle, we have one circumference of length around that circle. In one full circle, we have 2 pi radians of angle, and the relationship between those is circumference equals 2 pi times the radius. This relationship right here really entails all of these. And then finally, we have our expression for centripetal acceleration. There are no angular quantities in here, but we're going to be using this in this problem. Imagine we have a disk of radius 0.1 meters rotating about an axis through its center. In this problem, let's take counterclockwise as the positive angular direction. Imagine that at time t equals 0, this disk is rotating with an angular velocity of 10 radians per second, and that it comes to rest in 5 seconds, and it does so with constant angular acceleration. Part A of this problem asks us to find that constant angular acceleration. Well, we can use the definition of angular acceleration, and we note that for any time period in which the angular acceleration is constant, it must be equal to its average value. So we can actually use this average angular acceleration expression. So we've got the change in angular velocity divided by the change in time. The angular velocity changes from 10 radians per second at time t equals 0 to 0 radians per second at time t equals 5 seconds. So we're going to have 0 minus 10 radians per second, giving us negative 10 radians per second in the numerator, dividing by an elapsed time of 5 seconds in the denominator. And that's going to give us negative 2 radians per second. Since counterclockwise was our positive angular direction, this negative sign indicates an angular acceleration opposite that, or clockwise. Given this initial counterclockwise angular velocity, this clockwise angular acceleration will slow the disk down. So that's all consistent with our given information. All right, next we're asked to find the angular velocity at time t equals 3 seconds. To find the angular velocity at any time, we can use this in the case of constant angular acceleration. So our angular velocity at time t will be the angular velocity at time 0, that's the 10 radians per second, plus angular acceleration, negative 2 radians per second, times whatever time we want between time 0 and 5 seconds. We want time t equals 3 seconds, so we'll plug that in there. So plugging in 10 radians per second, negative 2 radians per second, and 3 seconds. We can take this and put it here, and that gives us 4 radians per second. We see the effect of the angular acceleration is basically to bleed off 2 radians per second of angular velocity every second. So in a time period of 3 seconds, we've bled off 6 radians per second worth of angular velocity. Subtracting that from 10 radians per second, we get 4 radians per second. Okay, let's move to the next question. We want to find the angular displacement for the first 3 seconds of motion. To do that, we can use this expression. So the angular displacement for the first 3 seconds will be the initial angular velocity times the elapsed time. The initial angular velocity is the 10 radians per second. The elapsed time will be the 3 seconds. Then we've got plus 1/2 angular acceleration, that's negative 2 radians per second, times the elapsed time squared. Again, that's the 3 seconds. If we want to find the angular displacement for the first 4 seconds, we plug in 4 seconds. If we wanted to find it for the first 2 seconds, we plug in 2 seconds. But we want it for the first 3 seconds, so we plug in 3 seconds. So plugging all those things in here, we can put it right here. and that gives us 21 radians. I want to note that if we'd had no angular acceleration, and if the thing had just continued at 10 radians per second for the 3 seconds, we would have just had 30 radians. But because of the angular acceleration, we don't cover as many radians. That's this term here. So we end up with 21 radians for the angular displacement in the first 3 seconds. All right, so we've found some angular quantities. Now we want to find some tangential quantities for a point on the rim of this disk. So first, at time t equals 3 seconds, we want to find the tangential velocity. We can use this expression here. So at time t equals 3 seconds, we have an angular velocity of 4 radians per second. We can multiply that by the radius of 0.1 meters because we're considering a point on the rim. If we were considering a point somewhere else, we'd use the appropriate radius for that, but we want a point on the rim. So we have 0.1 meters multiplied by 4 radians per second. We can put that right here, and we get 0.4 meters per second. In a similar way, we can find the total arc length traversed for the first 3 seconds of motion. For that, we use this expression here, relationship between arc length, angular displacement, and radius. So for the first 3 seconds of motion, the angular displacement was 21 radians. We can multiply by the radius since we're looking for the arc length traversed by a point on the rim. So we'll have 21 radians multiplied by 0.1 meters. We can put that in here. And that gives us 2.1 meters of arc length traversed by a point on the rim in the first 3 seconds of motion. All right, let's move over here and consider the tangential and centripetal acceleration for a point on the rim at time t equals 3 seconds. First, the tangential acceleration we can get from this expression. So the tangential acceleration will be the angular acceleration multiplied by the radius for whatever point we're considering. We're considering a point on the rim, so we'll want 0.1 meters for that radius. The angular acceleration is minus 2 radians per second. And that's not just at t equals 3 seconds. That's for any time between t equals 0 and t equals 5 seconds. So the tangential acceleration we'll actually be finding not just for t equals 3 seconds, but for this full time interval. All right, so negative 2 radians per second multiplied by 0.1 meter gives us this. And we get negative 0.2 meters per second. I want to stop here for a moment and say something about the units. You may be wondering, how do I get radians times meters per second and get meters per second? Or how do I get radians times meters and get meters? And where'd the radians over here go? We got meters per second, but I had radians over here. Well, it turns out that radians are a dimensionless unit of measure. So you can take them out or put them in as necessary. To see that radians are dimensionless, let's look at this expression. Circumference, that's a length. Radius is a length. And 2 pi is the full angle in radians. So this is 2 pi radians. But if this is length and this is length, that doesn't leave any room for units in the 2 pi. A radian is actually dimensionless. It's just a marker for a dimensionless unit of angular measure. So we can put the radians in or take them out as we need them. Returning to our calculation, let's find the centripetal acceleration component at time t equals 3 seconds. So we can use this. So we need the speed at time t equals 3 seconds. Well, we have the tangential velocity component at time t equals 3 seconds. The speed will just be the magnitude of that. So the magnitude of this will just be 0.4 meters per second. So we put 0.4 meters per second here, square it, divide by the radius. Again, we're talking about a point on the rim, so 0.1 meters is the radius. Plug that in here, and we get 1.6 meters per second for the centripetal acceleration at time t equals 3 seconds. All right, we can actually sketch those out. Let's imagine taking this picture right here. I'll put it right here. At t equals 3 seconds, let's look at this point on the rim of the disk. Now the angular velocity is this way. The disk is slowing down, so the angular acceleration is the other way. For this point on the rim, the velocity is to the right, the tangential acceleration is to the left, indicating that this point on the rim is slowing down. And of course, the centripetal acceleration is straight toward the center. I've not actually drawn these in proportion. This should be 8 times greater than this, and I haven't really drawn those proportions, so this is just an approximation. If we want to, we could go and calculate a magnitude and direction for this. So first I'm going to sketch those in. The magnitude of the acceleration will be the square roots of the sums of the squares of the components. So we need to take this squared, add it to this squared, and then take the square root. I can do that right here. And if I plug in the tangential and centripetal acceleration components respectively, I get 1.62 meters per second for the magnitude of the acceleration at time t equals 3 seconds. To get this angle, I could note that the tangent of this angle is opposite over adjacent, but opposite is actually this. So I could take this divided by this, that'll be the tangent of that angle, and then I could take the arctangent. So theta will be the arctangent of the ratio this over this. And I can put that here, and that gives 82.9 degrees for this angle here. I put this in absolute values in order to get a positive angle. Before signing off, I'd like to briefly revisit the directions of our angular quantities. So for a problem like this, it's perfectly adequate to specify directions as counterclockwise or clockwise. We specified counterclockwise as the positive directions, so clockwise was the negative direction. So our initial angular velocity was counterclockwise positive, our angular acceleration negative, that's clockwise. But in more complicated problems, it's convenient to specify angular quantities as vectors, and I want to show you how that works. So let's first consider this angular velocity of 10 radians per second this way. To get the corresponding vector, you take your fingers of your right hand, curl them in the sense of the angular velocity. Your thumb will then point along the axis in the direction of the angular velocity vector. So the angular velocity vector for this is out towards you. Now, for the angular acceleration, that was clockwise, that was this way. To get the direction of the angular acceleration vector, I do the same thing. I take my fingers, curl them in the sense of the angular acceleration. My thumb will then point in the direction of the angular acceleration vector. All right, so again, this angular velocity this way, that corresponded to an angular velocity vector out toward you. The angular acceleration in this sense corresponded to an angular acceleration vector in toward me. All right, so that's how that works for future reference. All right, that's all I've got for now. Thanks for watching, and I'll see you next time.